So hi everyone again, and thanks for joining me. I understand it's right after lunch, so I'll try to make it as entertaining as it could possibly be. My name is Federico Croce, and this is explaining classifiers in ontology-based data access. I come from the Sapienza University of Rome. I would like to start with a brief introduction that will introduce the problem. And so we know nowadays that machine learning is very efficient and has a lot of elegant solutions for a lot of different problems like machine translation, vision, autonomous driving, and many more. But there is an empiric rule that shows that the more a machine learning algorithm is accurate and the less we understand the magic, so why it works and how it works under the hood. And so deep learning is an extreme example of high accuracy and really opaque system, so a black box model. And this is a really intuitive representation of this concept. So if you can see, we move from, I don't know if you can you see my pointer? I guess you can. And so if we move from the linear regressions and decision trees, which are very interpretable kind of models, but unfortunately they don't have the same accuracy as more powerful deep neural networks. Of course, we would like something to be on the high spectrum right here, but as you can see, there are no solutions to that. So this paper will try to address this problem and try to give an explanation to the best working algorithm so far. Why should we care? So why is it even a problem? Well, for example, there are many different fields in which we are not only interested into the accuracy of the model. So just consider the COMPASS algorithm, which was used across the US in 2016 to predict future criminals. So it was applied to people that were already imprisoned, and it was used to predict the possibility that they will commit a crime later on in the future. Unfortunately, it was found out that this algorithm was very biased against Black people. So it was using ethnicity as one of the parameters to take the predictions. And we understand this is a serious issue in terms of ethnicity and in terms of interpretability of the system. A more recent example of this comes from just a couple of days ago. A sheriff, also in the US, was trying to use this algorithm to predict people even before they ever conduct any kind of criminal activities. So it was like Minority Report, if you guys are aware of the Hollywood movie. So it was applied to people that were completely clean, and 21 families singled out by the algorithm say that they were routinely harassed by deputies, even though they didn't do any kind of crime whatsoever. So we understand this is a very serious issue. How can we overcome this issue? Well, there are different solutions that are the state of the art up to now. This is one example. It's called LIME. It comes from a paper from 2016, and this is used as a local interpretation. So it is a kind of surrogate model that is built on top of an already working machine learning model. And it tries to predict locally. So you can see from the picture here in this particular space, it's trying to build a new machine learning model that is highly interpretable, such as a linear regression. So this line over here. And what it's saying, it's basically, I know for sure that close to this point, the complex algorithm, which is this fancy shape here, is working very closely to this linear regression algorithm. So I can explain this particular point by saying the algorithm in this point is behaving exactly as this linear regression model. This is a very good idea, I think, and it's working pretty well. But we are trying to propose a different approach, and our solution is a form of reverse engineering that is based on ontology-based data management, and it's trying to explain the model in terms of its global interpretation. So it's not trying to explain one particular instance of the model, but rather it tries to explain the whole model as it works under the hood, and it's trying to explain it by using the concepts of an ontology. So let me first try by introducing some preliminary notions, because I'm aware that it could be a topic that is not familiar for everyone. So ontology-based data management is usually a concept that is divided into 3 layers. And there is a layer which is the data layer that is actually the real data set that is taking care of all the practical stuff, let's say. Then there is the ontology layer that is a more formal description of the world and of the domain of interest. And there is a mapping that it's linking these two kind of layers, and it's trying to apply the formalism of the ontology to the data set. The user, it's up here, and it's supposed to use the system by querying over the ontology. So it's using the formal description of the world. It's not aware of what is working and how the system is working. It's using as an interface the ontology, and there is some kind of technique that rewrites the query that is issued by the user, and this goes all the way down to the data sources. So this whole procedure can work. There is a well-known notion of certain answers in this kind of settings, and it applies on what is called an OBDM specification, that is this triple of the ontology, the data set, and the mapping. And we say essentially that a tuple belongs to the certain answers of a query when it is in every possible interpretation that satisfies the database. So we say that for every possible model of the ontology and a given data set, if a tuple belongs to the evaluation of a particular query over that data set, we say that it belongs to the certain answer of the system. In this setting, we will consider the classifier to be just as an oracle. So we will really not take care of all the details of the classifier. And for us, it's just a magic system that every time we give it a tuple, it will outputs either +1 or -1. We're only considering binary classifiers. And so for us, it's very important that the whole procedure is completely agnostic with respect to the functionalities of the model, because we would like to be able to explain no matter what the technicalities of the model are, and we would like our procedure to be applicable to every possible kind of binary classifier. So for us, given any tuple of the domain, so any tuple on the data set, we would like this lambda function to be any kind of classifier that outputs + and -1. We will call lambda plus all the tuples that have been classified positively by this model, and lambda minus all the tuples that were classified as -1. Okay, so our framework will start with the notion of border. What is a border? A border is really intuitively just a smaller set of the whole data set that is developed by starting from one particular tuple in the data set. So we say that the border has a certain radius, which is an integer, is any number. And by starting from one tuple in the data set, we would like to move for at most r joins into the data set. And we call this new kind of data set a border of radius r for a particular tuple t. Let's consider this very simple example. If this is the data set and we consider A to be the tuple at hand, we can see that, for example, the border of radius 0 are just the atoms in the data set that contains A as a tuple. And then the border of radius 1 is everything that is reachable from the previous step and everything that is reachable with at most one join. Same thing for R2, and this is the meaning why the border of radius 2 is this set here, which is just the union of these other sets. So we are basically just removing these two from the data set because they're not reachable with at most 2 steps from starting from that tuple in that particular data set. We also want to introduce the notion of J-match. We say that a query J-matches a certain border when there is a certain border, sorry, of radius r of a tuple t, if that particular tuple is in the certain answers of that query with respect to that OBDM specification and that particular data set. So if that tuple belongs to the certain answers evaluated over the border, so this is important, it's not the whole data set, it's just restricted to the border. but if that tuple is in the certain answers of that OBDM systems for that particular query in the restricted database, we say that it J matches the border. So the whole query J matches the border. The goal of our framework is to find a semantic description of lambda. So we said that this lambda is any kind of classifier, any kind of machine learning model, or even just any classifier that is able to distinguish between a positive and a negative case. And we would like to find a semantic description that speaks in the language of the ontology. So it's in a way, it's redefining the whole model by using only the concepts and relations that are in the whole ontology. To do this, we would like to let the user define a set of predefined criteria. So our idea is that basically explaining something is not a unique definition. What it can look very reasonable for someone might not look understandable for others. And so our idea is to let the user define its own set of criteria, its own set of meanings of what a good explanation is for their particular task. And then by using a function that the user can, again, define depending on the particular task, we can have a quantitative measure of how much a given query meets the criteria. So we let the user, first of all, define what a good explanation is, and secondly, define how can we understand whether a particular query meets that particular criteria. Lastly, we have an expression that the user can use to sum up all the different functions for all the different criterion in the criteria set. So given that we have multiple functions, each function will evaluate how much a query meets one specific criteria. There is also one expression that sums up everything and returns only one value. And this is very helpful because in this way we can use only one quantitative measure to compare different solutions for the same problem according to the same criteria set. So in this particular example, we will take care, I will give you examples of possible criterion, possible functions, and an expression. And then I will illustrate a complete example that is working on our framework and so that I can show you what we mean by this all kind of infrastructure. Let's consider this first criterion. So we can arguably say that a user would like to maximize the number of tuples that are in lambda plus such that the query J matches the border. So what does this mean? Basically, we can argue that a user would like the query over the ontology to have the biggest possible intersection with lambda plus, because if that query is a good explanation of what the model is doing, we are supposed to have the highest number of tuples that are answers to that query that are also classified positively by the model. For the same reason, the user would like to minimize the number of tuples that are in lambda minus, because if the certain answers of that particular query are classified as -1 by the model, this means that the query is not a good explanation of the model because it's doing something that is not coherent with what the model is classifying. And as a third possible criterion, we would like this explanation to be as small as possible. So we would like this query to have the fewest number of disjuncts possible. By the way, the query where we are talking about are union-conjunctive queries. This is something I should have noted before and I forgot, sorry about that. So this is one possible function for the first criterion. We say that this function f1 is a way to understand how much a particular query meets that criteria. So if you can read it, is just saying I would like to divide the cardinality of the intersection of the answers to the query with lambda plus by the whole set of lambda plus. So I'm taking the proportion of answers of that particular query with respect to the lambda plus. This is again, this is a function that tells me how much I'm meeting the first criteria. Secondly, in a very similar way, I'm doing one minus the same kind of calculation, but this time is based on lambda minus, because again, I would like to minimize the number of tuples in lambda minus. And as a third component, there is this function that only counts, it has an inverse proportion with the number of conjunctive queries into the query, so that I can meet the third criterion. This is the last consideration, which is the expression that allows us to have one single value over the computation of that query. So this is just a weighted mean of the value of all the other functions. And we also have these three parameters, alpha, beta, and gamma, that tells me how much for the user the first criterion is important, how much is the second, and how much is the third. So the user could say, I would like to have this particular criterion as the very first priority. So I will give a big alpha to this because this is a weighted sum. And I would like the second to be the second best. And thirdly, I would try to minimize, but it's not as important as the other ones. So I would like to have a very small value of gamma for this particular reason. Let's see the algorithm working with a complete example. And we will start again with a full OBDM stack. So we will start from a data set, an ontology that expresses one specific domain of interest, and mappings between these two layers. The goal of this example will be to try to find a good explanation of a possible classifier applied to the dataset at hand. So consider this particular dataset. We have students of a possible institution, and these are possibly the ID number of the students. And we see there is this lambda function that is classifying positively this particular set of students, and negatively this only student, which of course could be also a set. Then we have other informations about the student. This is just a normal relational data set. Sorry, we have this other information. So starting from one student, we can do a join with this other table. And by this, we will know that this particular student is also studying math into this particular institution. And again, we know that this institution is in this particular location. So it's just a very simple data set talking about students, institutions, and locations of the institution. Suppose this is a particular ontology on top of that domain. So in this, we are saying that a math student is a scientific student, is a kind of scientific student. A science student is also a kind of scientific student. So it's a student that is studying something scientific. And these particular mappings are linking the tables in the data set with the concepts on the ontology. So this table N, we see if the second operators, if the second parameters is math, we know that we're talking about math students. So this is a way for linking everything that is in here with a concept on the ontology. And again, if this is science, we're talking about science student. And these are just basically renaming of the two tables. So it's just a basic renaming into the names of the ontology. The first step that our algorithm is taking care of is building the borders of a certain radius. I would like to notice here that the bigger we choose this radius, and the more information about the whole data set we are taking care of. So we possibly will have more explanations, but we will also have more complex explanations because it's linking different, it's linking a bigger data set, and it's having more information to take care of. So having a lower radius will help in having smaller and more intuitive explanations, but we are also taking the risk that no explanation is possible because we are only considering a limited data set. In this case, we are taking a radius of 1. And so starting from this table A10, we are allowed to do only one join. So starting from this, we can go up to this and up to this. So it's only one possible join. We are not allowed to do two joins. Notice that this was already available into the data set. So we're not moving further from this. And so this is the border for each tuple. These are all the borders of radius 1 for that particular data set. Then by starting from each of these borders, we can consider one conjunctive query for each of these borders. And it's very easy to do. As you can see, we just rewrite all these notions. We just rewrite them into possible concepts and roles of the ontology by using the mappings of the system. And for this, we are following this procedure. It's called source to ontology rewriting, which is found in this particular paper. And as I said, it's just doing the chase of the border and is applying the mappings of the system to find equivalent queries that are expressed into the language of the ontology. Notice that this procedure is complete, so it means that it can lead to more answers. So it will have all the answers of the original queries, but it can eventually have more answers. So for this reason, we will need to evaluate each of these queries to find out which one is the best, and it matches the most with the classifications. Now, one problem that we had is that these queries, if we take the union of these queries, it will already be an answer, because this is already something that is expressed on the language of the ontology, and it will already be an answer. But the problem here is that it's too many information probably. So we don't really understand what the system is doing, because we're taking basically every possible tuple of the data set and we're just doing some renaming, and we are not really understanding what the system is doing. So one possible procedure to reduce the number of queries is to use the so-called query patterns. This is a very simple idea. So we will say that two queries have the same pattern if they are conjunctions of the same set of atoms. So we can just rewrite the former queries by considering the query patterns, and by substituting, that everything that has the same atoms, by substituting it into variables and leaving all the rest into constants. So this step is based on the intuition that similar tuples of the database will be described by similar properties. So if they have similar properties, they should be explained by the same query, and they are somehow similar for this reason. Yeah, so already said that. So by applying this concept, we could rewrite the original queries, and we can come up with only 3 queries that, as you can see, are using variables now. So this first query is taking care of all the other 2 queries, because it's substituting something that was different just in terms of instantiation of the tuple, and it's taking as constant something that was shared between these the two queries. So it's in a way it's abstracting a little and reducing to one single query. The last step will be to find the best possible query out of those 3 that we're taking we are taking care of, and we can do this by one step, which is at the moment the most computationally expensive, because we will need to enumerate and to compute the zeta score, which was the evaluation of the expression defined by the user for all the possible union conjunctive query that either only uses atoms that belongs to one query pattern, or uses at most k atoms, where k is the highest number of atoms in the previous query. And by using this particular procedure, we can show that the query scientific student X is actually the best explanation of this particular example, because it has also the highest score of 1.0. Of course, this is just a dummy example, but as you can see, we can find a very easy and understandable explanation by using the language of ontology. So the model basically was just saying, I will say something is positive. So a student is positive if it is a scientific student. Otherwise, it's a negative example. Just to conclude, as a conclusion, This framework uses the ontology-based data management to provide explanations to any kind of classifier. At the moment, we are only focusing on binary classifiers, but of course we can extend this to more general kind of classifiers. The short-term goal will be to explore possible optimization of the algorithm, because as I said, there is a very computationally intensive step, which is enumerating all the possible queries with particular query patterns. And as a future work, we will also need to include comparison with other kind of similar works, and to evaluate this system with real world scenarios, and possibly also testing the user expectations in terms of these explanations. And thank you very much for your attention. If you have some questions, I will be very glad to answer those.